Good morning and welcome to MAE 106 Discrete Mathematics with Probability. My name is Richard Coar and today's lecture is lecture 32 covering the binomial distribution. So it's, like we said, it's a distribution. So it's an important probability distribution that we see time and time again in probability. So it's kind of why we've formalized it. There's many distributions in probability theory, but we're going to look at this one in particular. Good morning. It's good to see people chatting. And hopefully the audio is coming through okay. I hope so. So it's an important distribution, and the reason why we call it a binomial, or well, we already know that from the root for bi, it means that there's generally two things. It has exactly two outcomes. So there's two outcomes. Excellent. And it usually means that there's, for this case, we usually have that there's either a success or a failure. Oops, and I don't want it as a T, it's a failure. I failed to write that correctly. Failure. There we go. Now, without kind of explicitly saying it, we had actually seen a binomial distribution. And so if we go back to last lecture, which was lecture 31, when we were working on examples of probability distributions, we had actually seen one. So if we flip back, let me use one example. Here we go. So we had looked at this one, which was, we were looking at the random variable x, and it was the number of sixes that appear when an ordinary die is thrown 4 times. So we saw that there was two outcomes for this. There was something where we got it, we wanted to roll a 6 so we could get this, or we failed to get a 6. So there is kind of our two outcomes that we had. So there's two outcomes, and something else that's interesting is that each of these, when we threw them, were independent. So the probabilities didn't change of me getting a 6 on the first roll, or me getting a 6 on the second roll, or the third roll, or the fourth roll. And the other thing was that we were doing the same thing over and over and over again. So the trial, what we'll call throwing the die, is the same in each case. So we're not, for instance, flipping a coin and then choosing a card and then rolling a die. Those are not the same trial then. It's changing. So just from this example alone here, we have a couple of important features about this. So for a probability, for a binomial distribution, there's 3 properties that it needs to have. So The first one is that there's two outcomes at each trial. It's either a success or a failure. Again, some people would put these in like danger quotes. The reason for that is it all depends on what you want to define as what a success is and what a failure is. So you can think of each trial like as a roll or selecting a card, something like that. The next one is that the trials are independent. So like in the case where we're rolling the die, the probability of the previous trial doesn't affect the probability of the next trial. And lastly, the trials are identical, meaning it's not changing. Like I said, it's not changing from flipping a coin to rolling a die to choosing a card. They're all the same. Okay. So I keep showing this. And we came up with this distribution at the bottom here. And there's a couple things that we start to notice here. We have some patterns. So first of all, you can see that there's the probability of success here, which was of rolling the die and getting a 6, and that's what we wanted. And there's the probability of not rolling a 6, and that's our failure. And we've decided that in this case, x is going to be the number of 6s that appear when an ordinary die is thrown 4 times. So that's why we have from 0 to 4. But notice that in each of these cases, we have here's 0 and 4, 1 and 3. Let me put a little 1 here. 2 and 2, 3 and 1, 4 and 0. So if you add these up, there's 4, 1 and 3 is 4, 2 and 2 is 4, 3 and 1 is 4, 4 and 0 is 4. We can actually come up with a formula for this. So in general, for this one, we have the probability of success. We had the probability of failure. And how are we going to do this, which is the exponents here? Well, if we look, it corresponds to the number of successes that we got. So the number of times that we rolled a 6. So what I'm going to do is I'm going to write this up here as x. The next thing that we can do for the exponent over here is that we know that that these exponents have to sum up to give me 4. And it's decreasing every time that this one increases. So that's how I'm going to write it. I'm going to write it as, I know that there's 4 in total, and I'm going to just subtract it, x from it. Which leaves us to this issue of these numbers in front here. I have 1, 4, 6, 4, and 1. Does anyone see a pattern with those numbers? 1, 4, 6, 4, and 1. Just in the chat. Does anyone see? The thing that I kind of notice is if we look at 2 here, there's 6. It's symmetric around here is around the 6 is 4 and 4, 1 and 1. What structure have we seen previously where the numbers were symmetric? Pascal's triangle, exactly. Yes, yes, good. So let me just go back here. I had Pascal's triangle, so we remembered that it had 1. Oh yes, and I always write it like, I should write it a little better. There we go. Look at that. So those numbers that I had written here, 1, 4, 6, 4, 1, show up again in this probability distribution. So let me just, should have over here 0, 0, 1, choose 0, 1, choose 1. Over here this would be 2, choose 0, 2, choose 1. 2, choose 2. So we have 4, choose 0, 4, choose 1. Okay. And everyone remembers this is Pascal's triangle. And to get Pascal's triangle, I take the two numbers, I add them, and I get the next number below. Same thing here. So if I just kind of draw this here, adding those two together, and so that had led us to using what we called Pascal's theorem. So if I add those two together, so I have n, so here is like say 2 and 2, here's 0 and 1, so that's the increasing part, and it is then just r plus 1 and n plus 1, so it's n plus 1, choose r plus 1. So there's Pascal's theorem. But just looking at this now, those are my numbers. So I have 1, 4, 6, 4, 1. What I'm going to do is notice that it follows the same way. So here's 1, there's 4, 6, 4, 1. So same thing, there's 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. So what I can do is I'm going to use 4, and each time I'm increasing the number of successes, it changes it as well. But it's just going to be depending just on what x is. So I'm going to write down here from our previous lecture. So while we did it as a table, we can express this quicker as a mathematical formula. So again, I'm just rewriting this again. And so this would be for x equals 0, 1, 2, 3, and 4. So given that formula, you can generate any of those from 0 to 4. So if you wanted to plug it in, say x equals 2, well, that would be 4 choose 2, 1, 6 squared, and then you would have 5, 6, and over here you would have 4 minus 2. So 4 choose 2 is 6, 1, 6 squared, 5, 6 squared. And again, matches what we had for number 2. It's also another reason why we call it the binomial distribution, is because it is using a binomial inside of the formula here. So there's the binomial part. There's the success, there's the failure, and we have in the exponent the times that this occurs. But why are we using a combination? Is because when we look at these, we don't really care about the order in which they're happening. So over here, we've gone through all the order. So for instance, I have, let's look at 3 here. So there's 3 successes, 1, 2, 3, but I don't care in which order that they've shown up. So there's 1, 2, 3 here, there's 1, 2, 3 here, 1, 2, 3, and that's it. So I don't really care about the order. I only care about all the possible ways that can happen, and I want to know what their probability is. So I don't have to worry about that. So what this is doing is that we're eventually leading ourselves to coming up with a more general formula. So let's go over to number 2. Here's page 2. So we had that formula again. So let me just try to illustrate here. So here's like the number of ways. Of getting X successes in 4 roles. And again, we're defining success as getting a 6, a failure not getting a 6, the second part was that the roles are independent. And the experiment trials are the same. So again, like I said, they're not changing. So over here, so there's our 3 conditions for that. Over here, here's the probability of a success. And that happens x times. So that is rolling a 6. Over here, here's the probability of failure. So that's not rolling a 6. And that happens not n, but 4. 4 minus x times. So with this formula, you can actually read through what is happening then. Okay, so generalizing then, let's keep this here. Let's say x is a binomial random variable. Number 1, we'll say that P is the probability of a success. And we'll say that 1 minus P, which is the complement, is the probability of failure. We're going to say that they're independent. They're identical. And we're going to say that there's n trials. So we can start to build it up just the way that we had done it previously. So we'll say that the probability of x equals a little value of x. So that's the number of ways of getting X successes in N trials. So that's what we want. So let's start with this. We have the probability of success. We're going to define that as P. So we'll say that P is the probability of a success. So I can put that down here. Let's say even though I've defined it. And we're going to say that we're going to raise it to the X. Again, this happens X times. We have the probability of a failure, so we have 1 minus P. Oops. Okay, there's the probability of failure. And looking up here, so over here we had the trials, the number of times that it was 4. So instead of using 4, we're going to use the variable n. So this happens n minus x times. And lastly, we just need to handle the binomial coefficient. So over here, that would be the number of trials. So over here was 4, but this one we're going to just let n be a variable. So there's n, choose x. So over here, that's the number of ways of getting X successes in N rolls or N trials. Okay, so now that we've generalized that, why is this so great, useful to me? Well, not necessarily to me, but I mean to you and everyone that's listening in. The reason for this is if you can identify the situation where you can use this binomial distribution, you don't have to draw this probability tree anymore. So you don't have to do this laborious task of having to construct the tree, of looking at all the outcomes, counting all the outcomes, and trying to construct the random variable anymore. You can actually just go straight to writing down the general formula for this. So you could write it down like this. If you had to you have this formula, you could write out the table still, but you didn't have to go back and construct that entire probability tree. So again, this saves time. you can identify it as a binomial distribution, you won't have to make a probability tree. And that's kind of another major theme in this course is, yes, you could do something brute force, like counting all the possible ways to line somebody up. But if you know the principles of counting quickly, you can just get to the answer very quickly. The same thing goes with this probability. You could write this all out, but if you can recognize and identify this as a binomial distribution, you can skip straight to the formula. And you wouldn't have to waste your time doing that. What else did we do in here? Did we? Okay, this one. Okay, so what does everyone think? Does this save time then if you don't have to construct a probability tree? I feel like I'm trying to sell something on television. But wait, there's more. Okay, so you don't have to, it saves time. You don't have to do a binomial probability tree. Makes it faster. What if I tell you you get some more for free? Here's the second one. There's a formula for expected value. So no more having to use sum up all those x times those probabilities. So you don't have to do that. There's a formula. I will tell you what the formula is. And also, what else? Well, with this, you also get a pair of steak knives. You get another set for your friends. But there's a formula for variance. So that means you don't have to use that variance formula, x equals. You don't have to then calculate the expected value of x squared minus the square of the expected value. So you're probably wondering, okay, tell me what the expected value is then. Here's the expected value. So it's the number of trials, so n, times the probability of success. So there is the expected value. I'll put this in pink. This is important. So what I can do is if I flip back to let's see this one. Let me quickly flip back to this one that we had done previously. So notice that we had, this is a different one. This is exercise 9.2.6. We had the total number of tails obtained in 4 independent tosses. So let me just take a small card here. So again, this one, this X, which is the number of tails obtained in 4 fair coin tosses. So this is 9.2.6. It's a binomial distribution. We have a P, which is the success. So again, you're going to get tails, but this is a fair coin, so it's 50%, or P is 0.5. 1 minus P then is 0.5. We have the number of trials is 4, so here's N equals 4. They're independent. And they're the same. We're flipping a coin. It's not changing from trial to trial. So they're independent and identical. So I can actually write out then the formula for this. This is 4, choose X, 0.5 to the X times 0.5 to the 4 minus X. Okay? But this also means that because this is a binomial distribution, over here I know what my expected value should be. It should be X equals N times P. So that is 4 times the probability of success, 0.5, or if you prefer, 4 times a half. So 4 divided by 2 gives you 2. And remember, we had calculated this by hand. So here's the expected value. We did all this work. Here's the expected value, X times the probability of it, X occurring, and we summed those all up, and we came up with all of them, and we found that it was 2. So we expected 2 tails in 4 tosses of a coin. We could have done this a little faster had we known that this was a binomial distribution, and we could have quickly gotten, instead of using the complicated formula for the expected value, we could just have used the number of trials times the probability of success, which gives us 2. So I'll just kind of copy this back down onto the card here. Here's page 3. So we had done again, we can that experiment was a binomial distribution. We had p was 0.5. So when it's not independent and identical, you still need to do it the way you tough it in the last class. Yes. Yep. And again, like I said, that matched it when we did it by longhand. So all x, so those x times the probability. Okay. Now, I have one last thing, because I said there was more. There was a formula for variance. So we had the variance. The variance is equal to, so I can have it written as varx or sigma squared. This is equal to n, so the number of trials, times the probability of success, times the probability of failure. I'll put this over here. Number of trials. Oh, I've already written it. I'm going to point down here. Number of successes. And over here, number of failures. So going back to that example, this was from yesterday when we were calculating the variance. So here's my card here. I have from 9.2.6. So again, the probability was of success was 0.5, failure was 0.5. There's n trials. So we did the calculation and we got 1. So if I write this down here, so here's the variance. I said it was n times p times 1 minus p, which is, so the trials times the success times the failure, the probability of failure. So that is 4 times, I'm just going to use a half, times a half. So you get 4 times a half is a quarter. 4 divided by 4 is 1. And that matches what we had here for the variance. And since we have the variance, we can easily do then the standard deviation, which is just the square root of the variance. So that's just 1. So we still match. So again, I could write that over here. That's the expected value. So over here we have the variance. And like I said, it's n times p times 1 minus p. Four times a quarter, so 4 quarters gives you 1. And again, that matched the longer calculation. In lecture 31, again, matches the longer calculation. In lecture 31, using, and I believe in that case what we were using was this formula. Okay, so to get to Stephanie's question, if it does not follow a binomial distribution, do we have to do it the long way? And the answer is yes. So again, be careful. If it fails any of the conditions, you cannot use the binomial distribution. Okay, and that wraps it up for the binomial distribution. Thank you everyone for tuning in on this Wednesday morning. I hope this was enlightening and will save you time when it comes to doing some probability questions. And there's the summary right there in one screenshot. Thank you everyone, and have a great day. If you have any questions, feel free to send me an email at my RMC email address, or stop by during the office hour later tonight at 7 p.m. Eastern Standard Time. Thank you everyone, and have a great day.